Okay, so this is the second half of the recording. So you can see that I got to slide 14. Now I'm going to explain to you how I got this confidence interval around the estimator using the empirical rule. Oops. Okay, so let's suppose for a sample of size 150, I believe that distribution will be approximately normal, right? So this means that I can use the empirical rule, right? So if I think the standard error, standard deviation is 0.02, so this is standard error. I'm gonna elucidate this a bit later. I can actually compute the people. So because of the empirical rule, I can actually compute a portion of smokers, the range of values the portion of smokers can take, basically. And so the empirical rule says the following. It says that 60% of the data is, one deviation from the mean. And it says that 95 is within 2 deviations from the mean, and then 99, it says 3 deviations are 99%, are 99, it says that 99% of the data is within 3 deviations of the mean. Sorry, I kind of goofed up the last one there. So again, I'll repeat. 68% are within 1 deviation from the mean. 95 is within 2 deviations of the mean. And 99 is within 3 deviations of the mean, right? So this means what? Well, I showed you from last Tuesday that, well, actually, let me not refer to Tuesday. So let me just say the empirical rule says that you essentially, if you are within 3 deviations of the mean, this encompasses, like 99% of your data. This is the empirical rule, says that this is 99% of the data. Okay, slow. So this means that I can actually compute this. So if my data is 0.5, my data has 0.5, that's what you get on average, right? Minus 3 times 0.02. It's actually saying is that the possible, so when you're trying to ask where the actual true proportion of smokers are likely to sit, right? It's saying that the proportion of smokers, the true parameter that contains the portion of smokers is likely going to be between 44 to 56%, right? So the percent of smokers, or proportion of smokers in this case, so is 0.44 to 0.56, and this is actually this is 99.7 actually. 99.7% is is within here for possible thetas. Right, so the possible range of your thetas is pretty small, or it's between like 45 and like 55%, which kind of makes sense, right? So if a true population proportion of smokers is 50%, you shouldn't see like a very big range of possible values for theta hat, or for theta to be, unless your theta hat was very poor. So if your estimator is very bad, if theta hat is very bad, you may get either a wide interval, or alternatively, you get an interval that does not cover theta. You can see that in between this interval is the true theta, which is a half. Now, it's possible your interval is poor and that it doesn't contain a half, or it's too wide, but that shouldn't happen too often if you sample in a very good way, though. If most of your samples are representative, you should not see an interval most of the time that doesn't cover the true theta, right? In this case, it does cover theta. Sometimes it can, sometimes it can be off. So you can imagine, for instance, that if you compute a confidence interval for, theta is equal to 0 or theta is equal to 1.0, you'll get some ridiculous confidence intervals, but that really shouldn't happen too often, right? So it shouldn't be the case that too often you get a very terrible confidence interval that doesn't contain the true parameter, basically. Okay. Now let's consider that I have that, let's suppose I get one sample. Let's suppose I have a sample of n persons. And within that one sample, I got an estimate of 0.61. Now, this is not the greatest sample because we know the true theta is 0.5. So this sample didn't do a very good job, basically, right? If theta is truly equal to 0.5, then theta hat is really off, basically. This can't happen too often. If your sample is truly actually representative, right, then if you got a theta of 0.61 and you hypothesize your theta is 0.5, it's more likely the case that your actual population parameter is probably not 0.5, it's probably something else, and your initial guess was bad, basically. So to repeat again, if we know, for example, that our true theta is 0.5 and our sample gave us 0.61, then probably this sample is not very good because it yielded a theta hat as an estimate that's really off the true theta. But if we assume that our sample is truly actually representative, if we actually truly got 0.61 consistently as an estimator from an unbiased, from a representative sample, right? So if our sample is representative, it keeps systematically getting a very large theta that is far from what we hypothesized, which is 0.5. Then maybe our initial guess, or we could have actually made a mistake with our initial guess at the population parameter. Maybe it's not actually 0.5. We have to amend our initial hypothesis. This is actually the basis of hypothesis testing, right? So in hypothesis testing, you guess what you think the population parameter is, and your observations, your data is your evidence, basically. Or the data is the evidence, and it's possible that you messed up, basically. It's entirely possible your data shows your initial guess is wrong, right? And you have to amend it. This is the basis of hypothesis testing. You can imagine it. You throw a hypothesis at what you think the population parameter happens to be. If your data is actually representative and it's showing something different from what you actually saw at the population level, then you probably made it, your population parameter, your guess, the population parameter, your initial guess, what it was, is probably off because your sample doesn't give you that evidence that it's true. All right, so this is actually, again, the basis of hypothesis testing. And I'm going, so now it turns out that if I hypothesize that my true theta is 0.5 and my sample yields 0.61 as the estimator, the odds of seeing theta hat equals 0.61, if the true theta is actually 0.5, is like less than 1%. Right, so you can imagine if you go back here, the odds of seeing 1, given that the true value is 0.5 is 1 over 6. The odds of seeing 0, given that the true value is like half, is 1 over 6, and the odds of seeing a half is the biggest, basically. So what I'm saying here is that if it's truly the case that 0.5 is my actual outcome, the odds of seeing 0.61 in the sample is like less than 1%, basically. Why is this the case? This is a Z table and it's to be continued. This is hypothesis testing. So TBA. Don't worry about that for now in regards to the quiz. This is me getting ahead. So this is TBA. You don't need to know this third line here. These last 2 points is it to be continued? Like why is it 0.03? How do I get that number? To be continued. What I'm actually saying is that the odds of seeing this particular outcome is very, very low. So that would tell you your initial guess of 0.5 is probably off. if you yield a sample estimator that's high, that high when you have a representative sample. Right? So sampling distributions actually reflect the sampling variability. What do you mean by that? Again, every time you sample, you're going to yield a different sample of size n, right? You cannot get the same, you're not going to get the same sample each time you did. If you truly did a simple random sample, you cannot achieve the same sample of size n. Now, the issue is that if you really extract different samples of size n, this has to insinuate that your actual estimator for each of the different samples will actually change. Basically, you cannot have the same statistic from sample to sample, because the sampling units and your actual sampling units across each sample are not consistent. They're different. So you're going to yield different estimators across each of the different samples. And that means every estimator for the population parameter, for every estimate, is in fact different. Or you're going to get different estimates of the population parameter between samples. Now, this thing here is the variability. That is the sampling variability. The fact that you sample different sample size n each time you do a simple random sample and you yield a different test statistic, a different statistic from those different samples, is what creates that distribution. A distribution is created because you have a random process. The random process is coming from the randomness of your samples. And because you have different random samples, each time you're going to yield a different statistic for your different samples. That is a sampling distribution. You have a distribution of different samples, which yields different sample statistics from those samples, basically. Right? Now, obviously, it is literally equal to the relative frequency of observing a particular statistic if you repeatedly sample different samples of size n. So if you take different samples of size n, some of the samples will have the exact same estimate. As we saw with the smoking example, four of the six samples had the same estimate. 2 out of the 6 did not have the same, right? Now, the frequency of seeing the same statistic across different samples is what is creating the sampling distribution. Some statistics are more common across different samples than others. Some statistics are very unlikely. Like in the example of smokers, seeing a 0 and 1 are very unlikely because if you have a representative sample, most of the time you shouldn't see estimates that are very far off from the truth, basically, right? But this is what's creating the sampling distribution. If you have not sampled more than once, I'm going to repeat this again. If you have not sampled more than once, you have no sampling distribution. A sampling distribution comes from sampling more than one sample and obtaining different estimates of the actual population parameter from each sample. If you only have one sample, if you only sampled once, you only have one statistic. That is a sample data distribution. A sample data distribution is only one realization of a sample. And in this framework, you have no distribution. A distribution must occur only after you repeatedly sampled different samples of size n, and you calculate the test statistic for each sample. Now, the frequency by which particular values of a statistic repeats itself across different samples is creating that distribution. In the example of smokers, you had the same value occur 4 times. That was a half, and then 0 and 1 only occurred once, basically. And that is the distribution we created there. So let's put this to a context that we're probably gonna see a lot, which is the sample mean. And in fact, I'm pretty sure we started with sample means in this course. So consider that we have a population mean mu and a population standard deviation sigma. Because you cannot compute mu, you cannot compute sigma, because remember that sigma is related to mu, it's a function of the mean. So because you cannot compute mu, because you don't have all the population units, you also cannot compute sigma. Now, we can only compute the estimates. Y bar is an estimate of the mean, basically, right? Now, if we draw a sample of size n, we can compute the sample mean by taking the sum of all the observations and dividing it by n. So this is the sum of all the observations, right? Sum of observations divided by n, right? Notice that it is a function of the sample. It's the sample you extracted. Even though if you repeatedly sample a different sample of size n, the denominator is going to stay the same, right? So if you keep sampling different samples of size n, the denominator is going to remain the exact same, right? Because you have a fixed size n and you keep changing the sample base versus random sampling. However, the yi's are going to change across each of the different samples because the yi's correspond to different observational units, which are changing across each sample. So even if you have 10 different samples of size 100, well, your denominator is going to be 100 across different samples, the yi's will change basically. That's why it has to vary from sample to sample. And because your sample mean varies from sample to sample, it is itself a random variable. It's the randomness of this y bar is coming from the fact that you keep changing the y bar according to your sample. So because which particular y bar you get depends entirely on which observations you actually extract. It depends on the observational units. Then in this way, it's a random variable basically because it's going to keep changing the sample of y bar each time this y bar is changing. So you're gonna get different units each time. You get different y bars each time, right? So let's see how this is working. I suppose in this particular stats course, the prof had a midterm average that was pretty bad. So they had 112 students in their course, and they know of the true mean for all their students is 41.17. So the class didn't pass the midterm on average, right? And it had a standard deviation of 17.47, right? So most of the scores are, if you use the empirical rule and you assume that it's actually normal, we don't know that. So if you assume that it's normal and use the empirical rule, we should not, because we don't know. I mean, we were not told in the question what the actual the distribution of scores, or we don't know if it's normal. But I'm going to say if it's normal, we don't know. If you 17.47 is about 20 basically. So if you add 20, you subtract 20. Within one deviation from the mean are the scores that range from 20 to 60. All right, so class didn't really do very well on average. Anyways, we know that the true parameter is 41.17 if you take the sum of all the students basically. In this case, we can actually compute the true mean because it's very finite. There's only 112 students. Now let's suppose you draw a sample of size 9 students. So about all the grades, you took a sample of size 9, and then you compute the mean. Well, notice that you could actually get y bars 41.5. So notice I put y bar because now I'm computing it. It's an estimate basically. It's no longer mu because it's an estimate at the sample level. When you add up all those 9 marks and you divide it by a total sample size, which is 9, you get an average of 41.57 or 59, which is actually pretty close to 41.17. It's pretty close. So you can see that not bad, right? So your sample's estimate of 41.59 is pretty close to 41.17. It's overestimates slightly, but it's pretty close. Now, if you take a second sample of size 9, you cannot yield the same y bar because now you have 9 new different units. Their mean is 41.11, which is even closer, right? So you can see that even though they yield different y bars, they should still be kind of similar to what you saw at the true population level. You shouldn't have radically different means if your sample is representative. You truly sample in an unbiased way. You just truly did a probabilistic sampling. You shouldn't get y bars that are too far off from the true mean most of the time. Sometimes it can happen, but not too often, basically, right? So what we're really saying is that you can see the Y bars fluctuate around the population mean. Like literally they're fluctuating around the true mean, which is 41.17, right? Sometimes they're smaller, sometimes they're larger, but most of the time they're close to mu basically. What are we actually saying? We're saying that if we repeatedly sample, or if you literally sample many times, most of the time it's going to converge to the mean mu. And I actually did a demonstration here. I think I lost it, but when I showed you that, for this example of smokers, when I showed you that when you take the expected value of all those smokers, so if you go back on the actual recording, I did the following. So the expected value of the X, which is actually equal to, and I guess I should say expected value of theta hat. I said it's sum over all theta hat times probability of F theta hat equals a particular value of theta. Right. I said it was the following. I said it was like 0 was an outcome and I had 1/6 probability. And then I said that 1/2 was an outcome. It happened 4/6 times. And then I said that 1 was an outcome and it happened 1/6 times. And then the average is a half. So on average, it actually goes to where it's supposed to basically for the smokers. That's what we're saying here. If you repeatedly sample many different samples of size little n, on average, the expected value of your Y bar should be mu. So in this example here, the expected value was this, which is theta. So it actually converged at where it's supposed to. You don't expect that your actual estimate will converge to something that doesn't make any sense, right? So you don't expect it to converge off of mu. Most of the time it should converge to mu unless you messed up basically, right? So it shouldn't converge off of mu too often unless you truly messed up, right? So this is something where we have to keep this in mind, right? So most of the time, if we truly had a representative sample, it shouldn't peak off of what it's supposed to, right? And in fact, you can ask yourself, how many different ways can you get a sample of size, how many different ways can you get a sample of size 9 from, like, let's say, 110? And I don't want to do the math behind it. Okay, so I don't know if any of you know factorials, but like, I'm not going to ask you to compute this, but generally speaking, I'm asking you how many different ways can you get it. So if n is big N, 112, this is me being a bit of a geek, I'm sorry. It's like 112, choose 9. It's like 112 factorial divided by 9 factorial, 112 minus 9 factorial, which is a very big number, which is certainly bigger than, like, it's very big, it's large. I don't have my calculator, it's a pretty large number. Right, so there are you can get many different permutations of size 9. And if you take the mean of those permutations, like if you literally add up all the possible Y bars from each of those permutations of size 9, it will converge to 41.17, which is the actual population mean. Right, so it will do the same thing that we had here. Oh, where'd it go? Oh no. We'll do the same thing. Hi, where did it go? Oh no, did I lose it? Well, this sucks. I think I may have disposed of my cute little example, but you saw that I illustrated, which I think I kind of deleted. Sorry, guys. I showed the expected value of, like, theta hat for the smokers was a half, and the same thing will be true for the sample mean Y bar. When you take the expected value of that, like, you literally sum of all the possible. When you take the weighted average of all the possible outcomes, so if you look at all the possible outcomes, two of them corresponding to 41.59 and 41.11, but of course you have many more possible outcomes than these two. When you take the weighted average, like I did with this example here, right, it will converge to 41.17. The only reason why I don't do it is because, like I said, 112 choose 9 is too big. There are too many different possible samples of size 9 to actually literally manually code through this. Because I cannot compute all the possible samples of size 9, I cannot do it for you guys as a demonstration, but ideally what we're going to do is we're going to compute every single possible sample of size 9 and compute all their means as we did with this one and this one, and then create the same distribution as we did up here, where we sum up all the possible ways, look at all the possible outcomes you can get, and then how many times each outcome occurred. Because maybe 41.59 happened more than once. Maybe this happened in more than one sample. Maybe this happened in more than one sample, but there's a frequency of times at which each of these particular outcomes happen. And we can, after we have this distribution, we can do the same thing we did here to get this half, and it's going to end up being the exact as 41.17 because it's an unbiased estimator of mu, basically, right? Now, I did say that on Tuesday, one thing we look for when we talk about an estimator that is both accurate, and I use the game of darts. I said it should be accurate, where when you throw darts, you want it to be always in the center, as well as precise, meaning that like, just because you got the center sometimes, if you're really off the dartboard some other times, it's not good enough, right? So the example I gave was like when you play a game of darts, and you know, like you have this bullseye and stuff, and then sometimes you are in the center, but other times you're out here. Sometimes you're accurate, sometimes you're not. What you really actually want is to be both accurate and precise. You want to actually always be in the center for the most part, like, or around the center. You want to kind of be like this, more so than the first example. So that is referring to the efficiency, which I also brought up last class when I should have brought it up next week. But this is the notion of a standard error, basically. The error comes from the fact that each of the different samples have a variability on it. And so the variability between your different samples does yield an error, basically. Because you can see visually here that the Y bar is changing for each sample because you get a different sample of size 9. You can't get the same estimator, right? Now, because it keeps changing, there's an error that comes from the fact that Y bars are not the same across each sample. That is why you can actually see it's called the standard, so sigma squared of Y bar is actually equal to the variance on Y bar. And the variability, i.e. the variability on Y bar, right? There's a variability that comes from the fact that you can actually visually see you don't get the same sample, the sample estimate each time because your sample is changing. That is the variability, basically. Now, ideally, you want this variability to be small, basically. You simply don't want a very big variability on your estimator. There are things we can do to reduce this variability. And of course, when you take the square of that, you get the standard error, basically, right? So the square of that, let me put this somewhere else, actually. Let me not do this. I'm going to do like a consequence thing. So this is the variance, and then therefore the square root of this variance on the estimator is, you know, it's standard deviation, standard error, actually, to be honest, it's a standard error on Y bar. Now, there are ways to reduce this variability you tend to see in your estimator. The variability coming from the fact that obviously your sample is changing each time, so your estimator has to change. You would want to increase the sample size, because when you increase the sample size, notice that if sigma is equal to sigma, if sigma Y bar is equal to, this is actually sigma Y bar. sigma of y bar. So it's literally the standard error on your estimator. If the standard error on your estimator is a function of the sample size, you can see that the sample size in the denominator. If your sample size increases, you actually reduce the variability from sample to sample. What it's actually saying is that if your sample size is large, you're less likely to have variability across your samples. That makes sense intuitively. If your sample size is large, then each varying sample is likely to have units in common, basically, right? So you're likely to have members in common across each sample if your sample size is large, basically. You're more likely, right? So if you think about the example we gave in the beginning with the 12 people, right? If instead of sampling a size of like 2, I take a sample of size 11, the sample of size 11 will almost always have members in common. Because there's only one member that's not going to be the same across each sample, you have a very high overlap, right? So again, if you take a sample of size 11 from a population of size 12, only one member across each sample is not the same, right? So in this way, you have almost a very, very, very low standard error because your samples are very common or similar to each other, basically. So when you increase the sample size, you do decrease the variability across your samples. And when you reduce the variability across your samples, you actually reduce the variability across y bar. So I'm going to repeat again. When you increase your sample size, you reduce the way in which your samples vary from each other. And in reducing your sample variability, you actually reduce the variability of your estimator y bar, because that means if they have more members in common, the estimates for the sample statistics will be more common to each other, basically, right? So this is why when you increase the sample size, you can see that it will actually decrease the standard error on, it will decrease how much y bar varies across each sample because you have more members in common across each sample. So y bar will be closer across each sample to each other, basically, right? So it is also a function of sigma, which means that if at the population level you have a very big variability across your units, then you'll probably have a bigger standard error. Of course, for instance, you can make this standard error as small as you want by making your sample size big. But if sigma is very big at the population level, of course, your standard error will be bigger too. Because a big sigma at the population level means you probably have a very wide variability of the grades at the population level. A wide variability of grades at the population level would actually make it so that you may, by random chance, extract very different scores across each sample. And if you extract different scores across each sample, you're more likely to have a big, big variability across your sample. So it's a function of how big your sample is, as well as how much variability you have across the scores at the population level. If you have a big variability of scores at the population level, you're likely to actually pull out outliers in different samples. When you pull out outliers in different samples, that will influence your y bar, right? So again, if you have a big variability, you more likely have extreme values most likely. And this will actually make you more likely to pull out different outliers across different samples, which will make your y bar change drastically across different samples. So it's a function of how variable or temperamental your actual population sigma happens to be, and how big you make your sample size to mitigate that variability you see at the population level, basically. In general, you want a large sample size to make your standard error small though. All right, so as an example here, even though this is actually pretty big in terms of the variability, this is kind of big, which means that you probably have some really big scores in the midterm test and very small scores. So somebody did very poorly, much lower than 40%, and some people did very well, probably in the 90s or whatever, and it made the standard error very big. Like 20% standard error is pretty big, which means you have a wide range of scores. Now you may in sample 1 pull out all the low scores, or the low outliers by mistake, and in sample 2, you may pull out the big outliers by mistake, and then the y bars across the different samples will be very different because they're influenced by the outliers. But if you make the sample size bigger, you can actually shrink this, because this is still pretty big. Even this is pretty big because you only have a sample size 9. If you increase your n to 100, you're more likely to dilute those huge outliers, and that will make the standard error smaller. So you want to dilute the outliers. If you make your sample size bigger, your sample is less tempered or less influenced by those huge outliers you may pull out by mistake, and it makes it, you get a better sample, basically. So here's how it works, and we're going to show how we can actually make our our thing look better by just changing, making our sample size bigger. All right, so notice that this solid line you see here is the actual population distribution. I was right. Well, most of the scores are around 40. Notice that you have some people who got like huge scores out here. It's slightly right skewed. You have a couple of students that got some big scores out here in the hundreds and 90s. And you have some people, but less people who fail, but even some people got below like 20. So you have this proportion of people who got really poor grades. So this is, you see very bad grades here. And you have some huge grades up here. So you have a very volatile and very spread out population distribution, which you could by mistake pull out outliers across different samples, which will change your Y bar a lot basically. But anyways, if you can mitigate this picking of outliers if you actually increase your sample size, and we'll show in a bit. But notice that even though your population distribution is actually, skewed a bit, your sampling distribution is quite symmetric. And moreover, it actually peaks at the true mean, which is 41. You can see the mode is actually at 41 here. So it's peaking at where it should peak. So it's actually peaking correctly. So even though the population distribution itself is not actually quite symmetric, it is still peaking exactly where it should basically. And this is the beauty of like the center limit theorem and the sampling distribution. So the sample distribution does not care about what the population distribution happens to be. It will still peak where it should, right? So it's blind in some sense to the population distribution. It doesn't care about that too much, right? So there's a caveat there though. That's if you choose a sufficiently large sample size, right? So if your sample size is small, and for us in this course, small is going to be less than 30. So it's going to be less than 30. So sufficiently large means bigger than or equal to 30. If your sample size is really large, really small, you have no guarantee basically that sampling distribution will actually occur. It's really only for large enough sample sizes. So I will say that we have a slight right skew. You can actually see it, right? You can see a slight right skew. However, the sampling distribution is still symmetric. And actually, this is spelled incorrectly. Anyways, the distribution of grades is slightly right skewed, but it is somewhat symmetric a little bit. So it's not the worst skew you can ever see. It's somewhat normal. So that's why you were still able to get, the sampling distribution was still normal. Sample distribution, normal at size 9. So it's not that you couldn't have, you can sometimes get a sampling distribution that looks normal at small sample sizes. You're just not guaranteed that. So in this example here, it actually was normal when your sample size was just at, like 9, which is certainly less than 30. That's probably because this wasn't the most skewed. For very heavily skewed distributions, this probably wouldn't happen. All right, so it's not that it cannot happen at smaller values, it's just unlikely. So you really, in theory, want to make your sample size at least 30. Sometimes when you have, so there's a caveat here. If your population distribution is truly actually normal, you will see convergence to a normal distribution of the sampling. So a sample distribution will be normal if your population distribution is normal, even at sample sizes that are less than 30. So that's why this actually converged for a small sample size, because even though it's skewed, it's still somewhat symmetric. So this is not the most you can ever see. So this is why we saw convergence of the sampling distribution at only 9. It's because it's somewhat symmetric, but if it was very heavily skewed, you would actually need your sample size to be bigger, to be at least 30, basically. So let's see the effect of increase in the sample size, because like I said, you can certainly see that there's some very big and broad variability in the grades here. Now, in theory, you want to make your actual estimator have a very small standard error. Why is that? Because if I would just report this grade distribution to the actual committee, I would have to say that on average, students scored at 41.17 with a possible range of means of 20% to about 60%. That's kind of wide, actually. All right, so ideally, I don't want to say that, well, the possible range of scores are between 20 to 60. with a mean of 40%. That's still too wide. I'd like to compress that range, something between 40 to 50. I want to even make this range even more compressed, right? So if I want to compress the range of possible values for the true population mean of stat scores, I need to reduce my standard error, because this is when you talk about the margin of error. You need to make the margin of error smaller by making your standard error smaller. So you have to compress your distribution. You compress your actual standard error if you want to have a tight margin of error, right? So a margin of error, recall, is the thing we showed. Oh no, I deleted it. It's the thing we showed here, where I have theta hat minus ME, theta hat plus ME. Now this margin of error is actually going to be equal to Z times. So I'm going to claim this is true. This is the standard error. It's the quantile, and where this quantile is coming from, this is like next week. But it's a function of the standard error. So when your standard error is small, your margin of error will be small, and the range of possible values, for theta will be small if the margin of error is small, i.e. standard error is small. Okay, so you want standard error to be small because the margin of error is a function of the standard error. And when this margin of error is in fact small, you'll get a very small range of values for where theta can actually sit, basically. Right, so right now, this is kind of big. It'll tell you the range of possible values for theta is between 20 to 60%, which is kind of big. Now, if I increase my sample size to 100, notice this actually makes the standard error much smaller. It's only 1.47. What happens to the sampling distribution for such an estimator, right? So notice that it will make it more compressed, which I will show pictorially. But you can see that as your sample size increases, because this is the second one, you will actually get a smaller standard error, right? Notice that because the sample size for N1 is bigger than N2, right? So N1 is like 100, N2 is 9. It turns out the standard error is now smaller for this one than this one. This is why we care about the sample size. Now, what does that do to the distribution? Look at what happens. Notice that they are both unbiased. They both yield unbiased estimators. You will see that even when your sample size is only 9, it still peaks at 41.17, but there's a big range of possible scores, right? Notice that the range of possible scores is like really, really, really quite compressed for this one. It's like saying it's between 39 to like 45 or something. It's really quite small. So when I send this to my admin, I'll say that, well, the students had an average score of 41.17 with a range of possible scores of 39 to 45, 45, which is really bad. That would definitely never happen in our distribution, right? We are going to take the time to make sure we have a better average in our midterm, but this is what happened in this class midterm, right? So that's something to keep in mind. So they're both bell-shaped and they peak at the same mean, but we care about making the variability quite small. So this is something we have to keep in mind when we are thinking about our estimator. It's not just about the unbiasedness, it's also about making the standard error on the estimator very small. So then we get to the central limit theorem, and I'm going to pause. I want to show you guys a really cute demonstration from your TAs did that. So I'm going to actually do that. So let me pause, pull it up. Okay, I'm going to show you guys this file I made. So this is me doing an R file. So first of all, I'm going to say that so first of all, I'm going to say that I'm taking 40 samples from an exponential distribution. So I just want to point out that an exponential distribution is a right skew distribution. I'll just show you guys here. Oops. So let's say R gamma. Let's say I take R gamma 30 So you can, first of all, you can see that I picked a sample size of 30 because you can see I take 30 samples. Sorry. You can see my sample size is 30 because I told you that you're given some kind of guarantee in some level only when you have at least 30 basically. Now, because I know this distribution is actually quite right skewed, I should take I need to take my sample size to be a bit big, at least 30. And so let's see how this distribution actually looks. I claim that it's actually right skewed. And I don't know how many samples I took probably. I mean, yeah. Anyways, let me see for a second. So if I just do the histogram of R gamma, so 30, so sample has a 30, you can see that it looks quite right skewed. And in fact, if I make this bigger, so let's say I take 100, you can see it's really right skewed. So this is certainly not a symmetric distribution. If I just, like zoom in out, you can see that it's certainly very heavily right skewed. Right, so the problem is, so at the population level, this is a right skewed thing, much more so in the example we had of a distribution of grade, which is only moderately right skewed, even like mildly right skewed. So we definitely know that if you take a sample of size 9, you may not be given any guarantee about the shape of the distribution for small samples. Right, now I'm going to take 1,000 samples. So I'm taking 1,000 samples of size 30. So this is me taking the sample size is 30, and I'm taking 1,000 samples of size 30. Let's see what happens. So set.seed is me just saying I want to create the same sample each time. If I remove set.seed, it will just give me different samples each time, which doesn't matter. But anyways, I'm going to run this. You can see that I'm going to get different realizations of samples of size 30. Right. So each time you take a different sample, each time you do different permutation, you're going to get a different sample of size 30 from this function, basically. Right. Now, you don't need to know this for the test. I just want to demonstrate to you what the central limit theorem is doing, basically. So I know this is actually right because I just showed you guys that if I do what? If I take the mean of the actual distributions, basically, right? So first of all, let's look at the length of CLT. It's 1,000, right? Okay. So anyways, if I look at the mean of all these distributions, right, it's going to give me the following. So I'm going to get different realizations of size 30. And then when the theoretical mean for the exponential distribution is actually like 1. You don't need to know this. And the theoretical standard deviation is like 1 over root n. That's because the theoretical, remember that the actual sample standard error is this, basically. So the standard error for any estimator is like sigma over root n. That's why you have me doing the standard deviation over root n. So I'm claiming here that like sigma is equal to 1 over 1. You don't need to know this. I'm just showing you. I'm just doing it in an illustration based. I'm saying it's 1 over 1. And so this means that you can see that I'm taking 1 over 30, or over the square root of 30. Anyways, if I look at the histogram of this, what do I actually get? You can see that it's normal, right? So this is the sampling distribution. And actually this should be 40, not 30. Oops, I labeled this wrong. And it's 30. So I took a sample of 30, it's 30 different, cancel. It's a sample size of 30. But you can see that even though my population distribution is very heavily right skewed, the sampling distribution is symmetric, basically. And it peaks at the actual population distribution, which is 1. So the theoretical distribution has a mean of 1. And that's exactly where the sampling distribution peaks, basically. So I'm going to rewrite the code again because I was kind of looking at my own code myself while I was teaching it. So again, I'm taking a sample size of 30, which means that for every draw from the exponential distribution, I'm going to take 30 different samples. So I'm going to get basically 30 different samples, basically, sorry, 1,000 different samples of size 30, right? So which means that I'm going to get a mean for 1,000 different samples. So when it says I of 1 to 1,000, what it means is that I'm taking, right, a mean for each of the different 1,000 samples, basically. So this is why the length of CLT is 1,000. You can see that you're going to get different samples. So you get different sample means, basically. See that I took 30 different samples. So it's me doing the following: R gamma. I'm taking 30 different observations from an exponential. So you can give me 30 observations, but I'm doing this 1,000 times. I'm doing this 1,000 times, and each time I'm going to get a different mean, basically, because it's only one mean. I'm going to do this 1,000 times. You see that every time it goes to the function, it will give me a different sample of size 30, and it will compute the mean. And it's going to do this 1,000 times, basically, which means that CLT has 1,000 different means coming from the gamma distribution, where you have different permutations of observations. Now, I know that the actual mean for the exponential distribution is 1, and the standard deviation is 1 over root n. So what it's actually going to do is it's going to find the actual sample mean, right? And it's going to be coming close to what the population mean happens to be. So notice that when I run this, my actual sample my actual true gamma distribution is actually right skewed, but the sample distribution itself is actually quite symmetric, basically. You can see that it really symmetric, and it peaks at 1. Right? So it's peaking at the population proportion, which is 1, population mean, which is 1, and it's something that is actually heavily symmetric, even though the exponential distribution itself is right skewed. So it doesn't matter what the population distribution happens to be. The only thing it cares about is the sampling distribution. It only cares about the sample size, basically. It does not care about the underlying distribution, which in this case is heavily right skewed. All it cares about is how big your sample size is, because if I draw 1,000 different samples of size 30 from a right skewed thing, the mean of the average of those 1,000 different means is going to be peaking around, is going to have a distribution that is actually symmetric, and it will peak at the true population proportion. That is the central limit theorem. It literally says that we don't care what the underlying distribution happens to be. All we care about is a large enough sample size, which in our case is 30. You can see I actually demonstrated that 30 is a golden number, because you see that I get that guarantee. 1, the sample size is 30, right? So we care about a large sample size, which in our example is 30, right? And what it says is that the expected value is going to go to mu. So it's going to, whatever, it doesn't matter what your underlying population distribution happens to be, your distribution for the sample is going to be normal. As you can see here, it's actually literally and truly normal, right? With the actual mean that peaks at the true population mean, which is 1 in this case, right? And it has the standard error of sigma divided by root n, basically. So it doesn't care about what the underlying structure of the population distribution happens to be. All it cares about is that you took a sufficiently large sample size so that at the population level, at the sample level, sorry, you get something that looks symmetric, and is actually peaking at the true population proportion, right? So you have no guarantee of creating such a sampling distribution when it is actually not a large enough sample, basically. So this is actually what you're seeing happening in slide 13, right? It turns out that if I increase the sample size, it doesn't matter if the underlying distribution is right skewed or left skewed or whatever, it will actually truly be something that is symmetric if I take a large enough sample. So you can see that even at 100, it's symmetric, right? But if you keep increasing the sample size, what actually changes is this portion here. This sigma over root n will become smaller and smaller and smaller if you keep increasing the sample size, basically. And that's why you see this difference between this and this. While they both converge to mu, the mean, the actual shape of the distribution is changing as you keep increasing the sample size, because the actual standard error is going to change, right? So even though they're both symmetric, the narrowness of the actual distribution depends on your sample size, basically. Right? So Now, I did say earlier that if the sample size is, if your actual distribution is bell-shaped, then it doesn't matter what the sample size happens to be. Your sampling distribution will always be symmetric, but you do care if you have a skew to your population. If there's a skew, as you saw in the example I illustrated with the R code, where you had a population proportion that was actually right skewed, but the sample distribution itself was actually symmetric, you do care about the sample size, right? If the sample size is not exactly large enough, you may not get any kind of nice symmetric distributions we saw in our illustration. You may actually need at least a 30 if you have a skew distribution. Otherwise, you're given no such guarantee. And you can play with the code yourself and see what happens. And I'm going to pose it. If you change your actual n to like 9 or something, or let's n is certainly less than 30, you can see what happens if you get this nice shape or not. You might sometimes get it, depending on your seed. You might sometimes not, right? So you're not giving any guarantee if your sample size is reduced from like 30 to 9. Check and see what happens yourself. I won't spoil it. And I do want to do these two examples, but I feel like, actually I should do it now because I realize that people might watch this video. So I want to take a second, just take an access break. I'll take a 5-minute break and come back and explain these last two exercises. Okay, so this is the reason why I went over this example, especially the second one, is because I do want to elucidate to you guys how to use a Z-score when you do have a sampling distribution, because it's a bit different from so in week 6 we introduced like the Z-score, and I was thinking about this and I realized that the Z-score you compute for sampling distributions is slightly different from that in which you compute at the population level. If I give you, for instance, a mean and a standard deviation and ask you what proportion of like IQ scores is like less than whatever, given that it's normal, you would know how to compute the Z-score. But sampling distribution is a little bit different because you have a sample size as well to factor, which makes it slightly, we have to be a bit careful as to how we compute the Z-score. So this is the distribution of family size in a particular tribal community is skewed to the right with a mean of 5.2 and a standard deviation of 3.0. These values are unknown to the anthropologist. So even though we as the audience know the mean is 5.2 and the standard deviation is 3, the anthropologist hasn't seen that. They're blind to the actual values. So they have to estimate them themselves, basically. So, to take a random sample of 36 families, and she gets a mean of 4.6 and a standard deviation of 3.2. This is what she gets when she takes a mean of 36 families. Sorry, when she takes a random sample of 36 families, what she found from one realization of that sample of that family is a mean of 4.6 and a standard deviation of 3.2. And I want to point out this is a random sample. This means that she's only gotten these values from one realization of the data. We have not taken more than one random sample, right? Because the question is, identify the population distribution and its mean and standard deviation. Now, we can actually do this because you're told in the question, we as the audience see it, even though she is an anthropologist or he does not see it. Oh, actually it is she. Right, so we can actually say for ourselves that the mean is actually 5.2. We saw it basically, right? We know that the standard deviation is 3.0 because we saw those two numbers basically, but she didn't see that. And she knows the distribution is right skewed basically, right? Well. Now, what if I asked you, identify the sample data distribution? So this is one data. So this is when you have one sample, the mean and standard deviation. Now we can do this too, right? So we can say that the sample data distribution has a mean of 4.6, not to be mistaken with the population mean. This is one realization of the mean that she's gotten from taking a sample of size 36. When she takes another sample of size 36, which is different families, she will get a different estimation for the mean and the variance, or sorry, standard deviation. So this is only for one data. This is why when the question changes, it says identify the sampling distribution. It's not the same as a sample data distribution. Don't be tricked, right? A sampling distribution is the understanding that you've taken many samples of size 36, more than one, to create this distribution, which represents the relative frequency for the mean across different samples of 36. Sometimes the samples will yield the same mean, sometimes it won't, but there's a frequency of observations for a frequency of means when you look at all the possible samples, and you get a distribution that comes in which particular means are more common than others, right? So this is actually normal with a mean that is 5.2, not 4.6, because this is a central limit theorem. It's telling you that if you take multiple realizations of size 36, as we did here, we took multiple realizations of size 30, we got 1,000 different samples for the means. We got 1,000 different means for the samples of size 30, and we looked at the distribution, and it was actually symmetric, right? So when you take multiple different samples of size 36 from this right skewed thing, you will get multiple, maybe 1,000 different means instead of just one mean of the 4.6. We'll get 1,000 of them, and then we'll get a distribution of possible means that looks symmetric, basically. This has a mean of, that converges to the actual true population mean with a deviations given to you as 3.0, so the population level divided by root 36. All right, that's me using the central limit theorem. That's this. All right, so when you're asked about a sample data distribution, you can only answer that question, by the way, if the sample size you're given is bigger than 30 at least, or at least 30. If your sample size is less than 30, you cannot even say what the sample data distribution happens to be. And that's kind of important to note, basically. And so when I sketch the shape, it looks kind of like this, right? It looks like this. It's something that is normal that peaks at 5.2. And actually this should be a half, basically. So this should actually be somewhat tighter. It should always look like this, basically. It's something really tight. Like it shouldn't have, because the standard error is like 0.5. It's not that big, right? Okay. So the next question says, find the probability that her sample mean falls within 0.5 of the population mean. This question is a bit tricky. So this is actually the Z-score, but you may not know how the question is going. So I'm going to claim that falls within 0.5 of mu means that your actual Z-score can be negative 0.5 if your actual mean, if your sample mean Y bar is actually less than your actual population mean, or it could be actually positive if your sample mean is slightly bigger than the population mean. This is what they're asking. Falls within 0.5 of the mean can be in either direction, basically, right? So it's actually going to be equal to probability that that is less than 0.5 minus probability that that is less than minus 0.5. Now I'm going to use symmetry in the complement rule here. I don't have any of these numbers. What I do know is that it's that 1 minus probability that Z is bigger than 0.5 by the complement rule is the first one. And by symmetry, I know that this is true, basically, right? So these we can look up in the table. And if you do, you're going to see that it's 0.5. So 0.3085. We can see this here, right? It's going to be whatever this happens to be, 1 minus 0.3085, right? Minus the same thing. So I'm going to leave that to you guys to figure that out. That's that. And the last question, it says, if the sample were truly random, would you be surprised if the anthropologist obtained a Y bar of 3.0? This is a funny question because it's not always obvious where to start. But I'm going to claim that the best way to answer this question is to do the Z-score again, because you're trying to find the odds of observing a Y bar 3.0, given that the mean is actually 5.2. Because you'll be given the mean and the standard deviation, And you know, so the sampling distribution, so Y bar is normal with a mean of 5.2. And you know that from the previous example I did that you have 3 divided by root 36 is standard error. So we can do the Z-score because this is something that is actually normal. When you have a normal random variable, you can always make the transformation to do a Z-score basically. So that's what I'm going to do. I'm going to do the transformation to make a Z-score. So I did that here. You can see that I computed the Z-score here. Now, the thing that's a bit different here is that is this, because you're not used to dividing by root n. In general, it's actually going to be the following. For when you have a sampling distribution, it's actually going to be equal to Z is equal to Y bar minus mu divided by sigma over root n, because you have to divide by root n, because now you actually know that Y bar has the following distribution. It has a standard deviation that is given to a sigma over root n. So because you know that this is the actual distribution, you have to divide by root n. It's not the same as the typical Z-score where you just divide it by sigma. Because you have this factor of root n, you need to actually include that in your actual Z-score. This is why I wanted to show you that example, because some of you may actually drop this root n by mistake and you'll get a different answer than you're supposed to. And I don't want that to happen. So this is in general for sampling distributions only. If you're not working with the sampling distribution, it's the same x minus mu divided by sigma. But when you're working with sampling distributions, you need to divide by root n. That's something to keep in mind, please. So this is actually going to equal to -4.4. So I use a table again. Notice that the probability that is so the only way that 3.0 is extreme. So would you be surprised by 3.0? It's the same thing as saying, is 3.0 an extreme value? So if your actual mean is 5.2, 3.0 is like something here. So you're only interested in values that are as extreme as 3.0, because you're not going to look at the values that are bigger than 3.0, because some of them are actually, the mean itself is also bigger than 3.0. So you're only interested in the extreme values. The extreme values are the ones that are less than or equal to 3.0, because the ones that are above are actually closer to the mean, right? So you're not interested in the values, up here that are close to the mean, because it's going to tell you the common values. You're interested in the extreme ones that are behind 3.0. This is why I'm looking at the probability that that is less than -4 instead of bigger than, because I'm looking at the extreme values of my distribution. The extreme values are the ones that are far from the mean. So they're behind 3, not above 3. So that's going to be the same as saying the probability. So this is actually less than the probability that Z is less than -4. Why am I doing that? Because in the table I have at least 4, right? So this is going to be equal to it's less than the probability that it's less than the probability that so if you look at the table here, and I can actually probably draw that here. So what I'm saying is when we look at the Z table, we'll use to see when I transform this into Z scores, I have the following: 3.0. If the 0 is if 0 corresponds to 5.2 when I did the Z transformation, -4.0 is here, and -4 is here. So it's actually less than. So this is -4.0, and everything behind it. And -4 is over here. It's actually bigger than -4.4. Right, so that's why it's actually less than -4. The reason why I'm doing that is because I recognize that the following is true. Right, so I'm going to use my table. Probability that Z is less than -4.4, which is the transformation, is less than the probability that Z is less than -4. From the actual picture you can see here, this is -4, this is -4.44, -4.4, which is behind 4, which is equal to, by symmetry, the probability that Z is bigger than 4, which is equal to, from the Z table, it's this value here. It's -0.000317. Right, so let's recap. Would you be surprised to see a value like 3.0? You're not going to look at the values that are actually above 3.0 because they're too close to mean. The extreme values are 3.0 and below, basically. So what I'm really asking you is that, would you be surprised would you be surprised to see would you be surprised to see y bar less than or equal to 3 basically, right? So would you be surprised to see this basically? Right? So when I transform this into the actual Z-score, it turns out to be the probability that Z is less than negative 4.4 when you use a Z transformation. And that's when I use the table here. That's when I recognize that, of course, negative 4.4 is less than negative 4, which means it has a lower area behind it because it's more negative. The probability that Z is less than negative 4.4, you can see pictorially, it's actually less than the probability that Z is less than negative 4. So it's actually less than, the area above it is less than that of negative 4. And by symmetry, the area behind 4, negative 4 is the same as the area above negative 4, above positive 4, right? So this area 4 is the same as the area behind negative 4. And actually, to be clear, it's the same as the area, you know, like above 4.4 is equivalent to the area behind negative 4.4, but we don't have that in the table. Anyway, so that means that this is actually less than 0.000317, so it's very unlikely, basically. You're almost 0% chance of seeing an observation at extreme if the mean is actually 5.2. You shouldn't have seen that. It's very unlikely, is what it's saying, right? So we can actually use the sampling distribution to compute odds, which is what I did here. Yeah. So I just want to show this, and I will show it again next week. I just wanted to at least give it time to digest so you can watch it, and then I will repeat it again for those who are confused, because I know it's a bit of a confusing topic, and usually you guys like to ask me questions. So please feel free also to ask in the discussion, and I will absolutely take a look. Yeah, so feel free to ask me questions, guys, and I will take a look. Okay, so I'm going to stop now because that's it. Stop recording.